World. In this video, we're going to be talking about the quicksort, what it is, a demo, how it works, and we'll run our program. So the quicksort is like the merge sort. It's a divide and conquer sorting algorithm. The premise of the quicksort is to separate bigger elements from the small elements repeatedly. In some ways, the quicksort uses a similar idea to the bubble sort in that it compares items and swaps them if they're out of sequence. Lists in length of 0 are ignored, and those of length 1 are considered to be sorted, because you can't really sort something with one item in it. Let's start off with the video.
Here we have 7 cards that we're going to use to demonstrate the quicksort. What we first need to do is pick a pivot element. A pivot element is going to be one of these cards from the list, and we're going to use this card, and we're going to compare it to all the other cards in the list. If the card we're comparing happens to be less than the pivot element, we're going to push it off to the left side of the list. And if the card we're comparing happens to be greater than the pivot element, then we're going to push it off to the right side of the list. To differentiate the sides, we're going to use a wall. So to pick the pivot element, we could pick any card from the list. We'll just go for the last card, which is a 5. So we'll pull this card out, push these down a bit, and we can begin. So first we compare the 5 to the 4, since the 4 is the first element in the list. Since 4 is less than 5, we're going to need to push 4 to the left side of the wall. Instead, we can move the wall 1 up, and now it is on the left side of the wall. Now we compare the 5 to the 1. Since the 1 is less than 5, once again, we push the 1 off to the left side of the wall. We now compare the 5 to the 7. Since the 7 is greater than 5, the 7 gets to stay on the right-hand side of the wall, so we don't have to worry about it right now. Now we compare the 5 to the 3. Since the 3 is less than 5, we're going to need to push it off to the left side of the wall. But to do this, we first need to swap the 3 with the first element in the list. So, let's do that. And then we move up the wall by 1. We now compare the 5 to the 6. Since the 6 is greater than 5, it gets to stay. And we now compare the 5 to the 2. Since the 2 is less than 5, we have to swap the 2 with the first element. And then we move the wall up by 1. Now we have all the elements smaller than 5 on the left side, and all the elements larger than 5 on the right side. We can now take out the wall and place the 5 in. Now we have 2 sublists. We have these 4 numbers here, which are less than 5, and these 2 numbers here, which are greater than 5. We're going to need to sort both of these sublists now. To do this, we're going to use extra walls. So let's start off by looking at the left side first. We'll place the wall here, and we'll push these numbers off to the side because we're not focusing on them right now. We have to pick a pivot element, like from before. So let's pick the 2. We compare the 2 to the 4. Since the 4 is greater, it gets to stay on the right hand side. We now compare the 2 to the 1. Since the 1 is less than 2, we're going to swap it with the first element. And we're going to move the wall up by 1. We now compare the 2 to the 3. Since the 3 is greater, it gets to stay on this side. And we can now place the item where the wall is. And continue this process. We'll take 3 as our pivot element. We compare the 3 to the 1. Since the 1 is less than 3, we have to push it off to the left-hand side of the wall. We compare the 3 to the 2. Since the 2 is less, we push it off to the left-hand side of the wall. And we compare the 3 to the 4. Since the 4 is greater, it gets to stay where it is. And then we take out the wall and place the item. And there's the sorted half. Let's push these off to the side. Now we have these 2 numbers. This part is easy. We take our 7 and we compare it to the 6. Since the 6 is less than 7, you can push the wall up by 1. And since we've reached the end of the list, we place our pivot back down. And there you have it. A quicksort done.
Okay, so now that we've seen that video, let's start talking about the code. So here we have a function called partition, where we're taking A, the array, and size of the array as arguments. We have an if statement here, where if the size of the array is less than 2, we're going to return it because it would be sorted, right? Because you can't really sort an item of 1 thing or 0 things. So let's continue. Here we assign the pivot. Like I said in the video, the pivot can be any point or any element in the array. So here we have a random. Here's a random generator. It randomly chooses a pivot essentially. Here we have pardon me. Here we set the lowest and greatest index to the least and greatest indices in the array. So if I had a list of let's say 17 numbers, I would have my lowest index at the 0th element, and then I'd have my highest or my upper index, the U index, at the last index in the array. So that's where we're establishing that. Then we have this while loop here, and what this while loop is doing is essentially it's going to run until the upper and lower indices are equal. So we have our first while statement here, or while loop, pardon me, inside first nested one at least, where the lower index skips over elements smaller than the pivot, and the second one where the upper index, U, skips over elements greater than the pivot. And then whenever L is greater than or equal to, so whenever the lowest index is greater than or equal to the pivot, or whenever the upper index is lesser than or equal to the pivot, we swap using this right here. And then these two functions here make it recursive, so that this entire function here is going to keep on repeating itself until it eventually sorts the entire array. So now let's actually check out the program in the C++ code. Alright, so here we are in code blocks. We have our main CPP file, and this is the quicksort. We have our two F streams here. This input file is going to open random.txt right here, which has 10,000 random numbers from 1 to 1 million. And what it's going to do is it's going to read this file, and in this snippet of code here, it's going to perform a while loop where it's going to push in each number into an array, or pardon me, it's going to push in each number into the array with starting from 0, like here, starting from IRA 0 to IRA how many numbers there are. So it can vary. This F stream here is the output file. This is what the program is gonna print out once it's done. It's gonna create a random sort.txt file with the 10,000 numbers sorted. Here we have the quicksort function. The 3 arguments it's taking in is the array, the first index, and the last index. So obviously the first index is going to be 0, and the last index is going to be 9,999 because there's 10,000 numbers. So this gives you room to, like, let's say you wanted only part of the array sorted, you could change the numbers, right? So that's pretty cool. Here we have inside the quicksort we have an if statement where as long as the first index is is less than the last index or the upper index. This is so you'll understand why this is here later on. I'll explain it. Here we have int j, which is another array, and it's going to be equal to partition IArray p and r. So the 3 arguments once again: the array, the lower index, and the upper index. So that's another array. So it's going to run this function here. This function is up here, partition. If saw the pseudocode, it looks quite similar. It probably is almost the same. So here we're declaring our pivot. Pivot is, we're going to use the last number as a pivot instead of a randomized one, just so we can keep things the same or constant. We have a while loop, our first while loop, where it's going to run until the upper and lower indices are equal. Or pardon me, it's going to run until as long as the lower index is lower than the upper index. So once it's equal, it's going to stop running. Yeah. So here we have as long as IRA p, so p being the lower index, as long as this element is less than the pivot, then we're going to add 1 to p, the lower index. And then while the upper indice is greater than the pivot, we're going to subtract 1. We're going to keep on going down. And then if IRA P is equal to IRA R, P plus plus. So if the lower indice is equal to the upper indice, we're going to increase 1 to P, or the lower indice. Otherwise, if P is less than R, then we're going to do the switch here, or swap. And then it's going to return R. And then when it returns R, it's going to return R here, so it's going to be int j is equal to R in this function. And then it's going to run, this is the cool part. This is where it's recursive. It's going to run 2 quicksorts, or it's going to run this function twice, with one half, the left half, and the right half. So the number is lower than the pivot element, and the number is higher than the pivot element. And that's pretty cool. And it's going to keep on doing this. It's going to keep on, it's going to keep on doing this until, this is where the if statement comes into play. It's going to keep on doing this until the array is sorted. So, it's really neat. At least I find it pretty neat. Anyway, let's build and run. Might take a while. Oh, there you go. Wow, 3 milliseconds. So the sort is pretty quick. Here's the sorted file that it created, and that looks pretty sorted to me. Yep, there we go. Awesome.